Well, hello, everybody. We're back again. This is the introduction today of another displacement technique. This one is called virtual work. So we'll start today with virtual work for trusses, and then we'll evolve to beams and frames. So I hope everybody's doing well and the videos are working, kind of. Let me know if things are going well, if we need to have or try to have a Zoom session sometime where we can interact. Let me know and we can arrange one of those. So for now, I'm going to share my screen and talk to you today about virtual work. So you remember our previous techniques were called geometric methods, and that was direct integration and conjugate beam. So these are energy methods. It's called virtual work. And it comes from the application of what's called the principle of least action. And it's for forces and movements of mechanical systems. So this has a variety of applications throughout solid mechanics. So it's been used for a long time, maybe thousands of years. In fact, it was used by the Greeks and the Arab societies and the Latin Romans. It was known then as the law of the lever. Now, the technique that we're going to use today was first developed by Johann Bernoulli. And we'll give a little history of that. You know, I like a little bit of history. So I'll talk to you today about Johann and his son, Daniel. Daniel, you might be aware of from hydrodynamics. So the principle that we use today was first developed by Johann or John Bernoulli in 1770, also called the unit load method. When I was a young man, we called it the dummy load method. I guess that's out of fashion. So there's a picture of Johann. You can see he was born in 1667 all the way to 1748. He's a Swiss mathematician and really the beginning of a long series of Bernoullis that made contributions to mathematics and physics. And he's known to make contributions also to calculus, and he was Euler's student in his youth, so it's got a good connection there. Now in 1738, Johann and his son Daniel almost simultaneously published works on hydrodynamics. So there's Daniel down there at the left corner. Daniel and his father didn't have a good relationship. In fact, they both entered a contest, a scientific contest in Paris, and Daniel won. And Johann could not bear the shame of that, or even being compared to Daniel, and basically threw Daniel out of the house. So later on, it was found out that Johann actually plagiarized sections of Daniel's book, Hydrodynamica, into his own book, and then backdated it to try to get the credit for developing that. And despite Daniel's attempts, they were not able to reconcile their differences, and Johann died before they could get back together. So the one that you're familiar with is Daniel Bernoulli, and that's Bernoulli's equation that you use in our hydrodynamics work. Some of you may be familiar with that. If not, you'll be taking that course very soon. So a little background on the Bernoullis. Just to show you, you can see here that we have, let me get a little, so here's Johann at the head of the family. And then you can see there were several sons, and then all the way down, even into almost modern times, different Bernoullis. So there's Daniel. So there's the two that we know, but you can see there's been quite a few throughout history. So let's talk about how we would do this for truss work. So I'm going to derive this formula, but you're really not going to have to be responsible for that. When we're done, you'll be responsible for the end formula. But I thought this was kind of an interesting insight to how this works. So we're going to look at how virtual work will compute a component of displacement at a point in a structure. So you're not going to get a equation like we did in direct integration, kind of like conjugate beam. You're going to get that one component, a displacement at a point in a certain direction. So to do that, you have to choose then the point that you want and the displacement that you want that displacement in. So we'll say, oh, I want the vertical displacement at B or the horizontal displacement at A. So once you make that decision, then you can apply this technique. We're going to call it the virtual load method, but just again, a little history. When I was a young man, we used to call it the dummy load method or the point load method. So we're going to start by looking at two different kinds of systems. We'll call it the P system and the Q system. As you can see, the Q system will be associated with the virtual load. And then the actual loads on the system, the real loads in the system, in this example, I'll call it the P system. So as the structure deforms under the actual load, you'll get external work done. And so W for work, Q, and that's done by the virtual. So work is going to be, if you remember your physics, a force going through a distance. So this is going to be a balance of real forces going through real distances and virtual forces going through virtual distances, and then the combination of those two, real forces going through virtual distances and virtual forces going through real distances. So as you apply work to a system, as most elastic systems do, deformable bodies do, they will respond by displacing. And displacement is effectively strain energy. So we're balancing the external work done by the forces with the internal work stored in the system. And we'll assume that's a conservation. There's no loss of that. So again, you can see work, external work, W, internal strain, U. The subscript indicates, in this case, Q, that'll be the work and strain energy of the virtual system. And those will have to be equal. And that's the conservation of energy. So let's consider how this would work, a virtual work on a bar of our truss system. So here's a bar, as you can see. It has a real length. And it has a real force P applied. And you can see as it applies, the original point B will deform some amount. So there's my displacement P, real force displacement. So B moves from B to B prime. So that's the external work, a real force P going through a real displacement. Simultaneously, the bar itself is elongating, right? And that elongation is a measure of the strain. Remember, strain kind of change in length over original length, and that's kind of what this is going to be. So if I were to plot that, you would notice that it's linear. So this is a plot of P over displacement. So no load, no displacement, and you can see it goes right up this curve. So the area under the curve is the total work, the total energy done with this system. So real work done by a real force. At the same time, the bar, as you deflect point B, the bar in this case looks like it's elongating. And that force that it feels, the axial force due to the real force, and the bar actually elongates. And that's also a linear curve. And the area under that is a measure of the strain energy. And that is also something we can compute. And of course, we know that those two things have to be equal. So this is the work done by the real force and the strain energy by the real force. All right, so let's now look at displacements produced by the virtual force. Now you notice this system looks very similar to the last one, except now we have a virtual force Q applied. Remember, it's virtual, it's not real. It's not really active in the system. It's just a mathematical abstract. And when that does move, we would go through a virtual displacement due to that force. And of course, if B moves, then the bar would elongate and you would develop an axial force due to the virtual system. If the bar elongated, you'd have a length. And if you look at those things, again, you would see if I could plot the virtual force as a function of the virtual displacement, I would get some work done. And the work under that would be the work done to the force, work done by the force. So this is real work done by a virtual system. And then, of course, there would be real strain energy. This is analogous to what we saw previously. So if you'll notice, all the variables are virtual. And of course, that needs to be conserved also. Now, here's the real interesting part. Let's now consider forces of displacement produced by the virtual loads and real loads acting together. So look what we have here now. We can see that we have a real load P and a virtual load Q going through a displacement. And you'll notice that the force produced in the bar is a combination of those two, and then we have an elongation and a displacement. So now I've got a virtual force going through a real displacement. So what's going to happen with this? Well, now you'll see that as I apply, this is my virtual system, real work done by my virtual system. This is the real work added to it done by the work done by the real system. So you stack those on top of each other, and now you get this area below here, which is the work done by the virtual system going through a real displacement. Okay, same thing looks to be true of the total work done in the bar, the strain energy. So again, I've got this component and this component, and when I stack them together, I create an additional strain energy underneath, which is the strain energy of the virtual system going through a real displacement. And of course, those two things are the same. So what this in effect gives me now is I have a relationship between those hatched areas. So since the work done here has to equal the work done here, it gives me a different relationship. Oops, sorry, I went too fast. So now the real work done here is a virtual force Q going through a real displacement. That's the area of that thing, base times height. And the same thing is true for the strain. Oops, went too fast again there. So I've got a real force FQ, I'm sorry, virtual force FQ going through a real displacement. So let's see how that adds up. So now I put those two things together. Oops, sorry. So now look on the left-hand side. I've got a real force, a virtual force Q going through a real displacement, an internal virtual force going through a real displacement. So I've got like a virtual system you can see here, and a real system to the side. So let's see what this can do for us. Well, we can sum this up for all the elements in the truss. Remember, before our expression was just for one element. So now I'm getting the contribution of each bar to the entire system. Now this real truss, well, I can make an approximation for that. So I'm going to replace that with the real force F times the length divided by AE. So the force divided by times the length divided by A gives me this displacement. So now if you look on the right-hand side, I've got a virtual force and a real force, and then real things about the truss. Length of each element, cross-sectional area of each element, launch elasticity of each element. On the left-hand side, what do I have? I've got a real force, a real displacement at some point, and a virtual force. So I'm going to use this new notation now. We're going to use a lowercase n, which will be virtual forces, and an uppercase n, which will be real forces. And that notation will follow through the whole virtual work section. Whenever we talk about a force or a moment, the lowercase usually will represent the virtual system, and the uppercase will represent the real system. And I'll show you how this works in a second. I think an example will help clear this up. One more thing we'll do is we'll assume that our virtual force is 1. And that's where the unit load method comes in, unit being 1. So therefore, if I'm looking for a single displacement, single component, I now put my virtual load Q at the point in the direction I want the displacement, the real displacement. And I can compute that by creating this sum for the whole structure. So what does that mean for you? That means you have to do 2 truss analysis. One, define your n values, or the real forces. Then you do the structure again, remove the real forces, apply the virtual load, and you'll find the lowercase values. Do this summation, and you found the displacement at the original point. Okay, so let's look at an example. So I'm going to find the horizontal displacement at joint B of the following truss. You'll notice I have a value for E, and I also have values for the cross-sectional areas, and you should be able to get the length off of the diagram. So there's the only force in the system. That's my real force system. So the first job is to find the force in every element in this truss. There's 1, 2, 3, 4, 5 elements. So find 5 forces due to the real load, 60 kips. Now, since I want to compute the horizontal displacement at B, I need to come back and do what's the virtual system. So here's my real force system again with just the real load applied. And I'm going to find the bar forces in each of those. Remember, we're going to follow the same sign convention we had before. We're going to use positive for tension, negative for compression. And there are those values. So you see, there's my reactions. And then, for example, here, plus, that means that the force in AB is positive 80. And you know how to do that. You can do method of sections, method of joints, or more complex problems. You can even use SAP 2000 to do those very quickly. So now here comes my virtual system. Remember, I wanted the horizontal displacement at B. So at B, I put a horizontal force Q, remember that's the virtual force, and unit load of 1. Notice I've removed the real load, so there's no real loads on the system at all. There's just the virtual load. And then you can also see the reactions written here. For example, there's the virtual load in member AD, it's -4/5. So now I have my real forces and my virtual forces. Again, maintain those sign conventions throughout. Positive for tension, negative for compression. So now I'm going to create a table. So at the top here, I just brought back my real system. You can see here, that would be the P system. And then over here is the Q system. So I'm going to make a table. So I first labeled each of my elements, and then I'm going to fill in the real forces that I computed. You can see I'll just add those in. So those come directly from my, so you can see AB goes right in there. I do that for all of them. And then I do the same thing for my virtual system. So again, you can see AB here, it lands right there. So once I do my 2 truss analysis, my real system in my virtual system, I simply just fill in the table. Now I just need to do some geometry. So I look at my dimensions and I can put in the length of each one. I've converted those to inches to match the unit of my area. And then from the original problem statement, I know the cross-sectional area of each of the elements. So remember my virtual work statement is I need to sum the virtual load, the real load times the virtual load times L divided by AE. Now in this case, E is constant. So just to make it a little easier for myself, I'm not going to divide by E. So now I'm going to form the product real load, virtual load, length over A and hold off on dividing by E. So I'm just going to multiply in virtual load, length, and then divide by 4. And when I do that, I get this value. And then do it for each. Now you'll notice since I've got several virtual loads, this could go for real loads too that are 0, it makes those products pretty easy to calculate. In fact, they're 0. So I only get 2 non-zero values in this particular one. And remember, I'm going to sum those up. So when I do that, I get a summation in this case of 12,300. And this is going to have the units of kip inches. Of course, when I divide by E, which is kips per inch squared, I'll get a unit of inches. So there's my table. So let's go ahead and do that. So there's the numerator that I just computed. And I'm coming back and dividing it once by E. And you can see I get a pretty small number, in this case, 0.41 inches. And since I got a positive value, the fact that I chose my unit load to the right is confirmed. So there's my displacement for the truss, the horizontal displacement at B. Here's another example that we'll work through real quick. So I've got a truss that you can see here. I want to find the magnitude and displacement at D, which is here. So there's my real load system, a single point load at D. The values in parentheses are the cross-sectional areas of each member. So there's my real load system, which I solved for, and those are my values for tension and compression. So now I remove my real load and I do a virtual system for the vertical load, and you can see the resulting values of tension and compression for several members. And then I did it again for a second system for the horizontal load. And the reason I'm doing two components is I wanted the magnitude and direction. And you remember in 2D, I need 2 components. And here's the corresponding values of tension and compression in those elements. So now I have all the information I need, I can form this table. So what I've done here is I've, in one table, put 2 problems in. So first of all, you'll notice that I've entered in, there's all my real forces. And then for the vertical component that I did, these are the virtual forces for the vertical component. And then right next to them, I did the horizontal component. And the length of each element in inches, the cross-sectional area, and then now I'm going to form 2 sums. So you'll notice the first sum, real virtual length over area, that's going to just compute the part for the virtual load, and then a second sum for the horizontal load. So I'm really doing 2 calculations in one table. So that number again would be this times this divided by A. So I'm not using the horizontal value here. I'm using that in the second column, or actually the last column. And then complete that for the entire structure. Looks like I've got no non-zero values here. And then I'm going to sum these up to get the total contribution to the vertical, and then sum these up to get total contribution to the horizontal. The numbers are just coincidentally close, but there's nothing there that's that you should take from that. Just numerically, that's the way that came out. So then when we're done, I divide by, as you can see, E for each one. So there's my horizontal force. It came out positive, so I did assume correct to right. And then this is the vertical component. Also came out positive, so that's its value. I assumed down for that one. So there's my two components, my horizontal component and my vertical component. And just to complete the problem, I just laid those out at point D. I went ahead and vector summed them together so I can get now the total displacement, which ends up being about 0.27 inches. And then just to give it a magnitude, I measured the angle as 42 degrees, and I measured that from the x-axis. So now I have magnitude and direction, total displacement at point D. Okay, so that's it for trusses. I'll work some more problems later, and hope everyone's doing well. Now I'll stop the share here and just come back to you and say, let me know if you have any questions. I'll give you a couple problems to do this. You can use SAP 2000 to do your truss analysis. Don't try to do it by hand. And let me know how things are going. Again, call me at home or send me an email. Okay, until next time, I'll see you.